Yes, thanks for the introduction. I have the pleasure of presenting this topic to you. I was introduced, I'm Olaf Hartwig, I'm from the Max Planck Institute in Hanover. So L0.5 to L1 data, what does that mean? I gave you a little overview from the Red Book. As you all know, LISA is this constellation of 3 satellites, and the way it is envisioned to work is that we first receive these measurements using ground stations from Earth, producing the so-called level 0 data. And this will be the raw data from the satellite, so it will not be ordered in time. It might contain some artifacts and so on. So there will be some initial calibration of that data, correcting for these effects, which is where this 0.5 comes in. And I will not speak more about those 0.5 in the remainder of the talk. Then we do some processing of these spacecraft signals, which is what this talk will be about, to produce the so-called level 1 data, which are these infamous TDI variables you probably heard about, the data streams from which you can actually directly recover gravitational waves. And then there's a bunch of other stuff going on that many of you are working on, but I will not talk about further in this talk. If you want to know more about the organization of where this is being developed, there's a poster by Antoine Petitot on the DDPC, the European Effort for Data Analysis. Now, I tried to sneak in a small animation of LISA, although you probably have all seen it. And the reason I show it is because many of the things we have to do in L0.5 to L1 actually are related to these orbits that LISA has put on. Although they are remarkably stable, that it stays more or less a triangle, they're not perfectly stable, which is why we have a problem with laser frequency noise. It is not cancelled to the level that we need, which I will explain in a bit. Another problem that stems from these orbits is that they are also, the spacecraft, as you can see, are not stationary with respect to each other, but they have relative velocity, which introduces Doppler shifts, which means that our signals are actually time varying, megahertz speed nodes, and that induces problems with clock noise. And the third problem is that these little points there are actually not points in reality, but they're actual spacecraft. They are 3-dimensional objects, and you have to be very careful about tilts, which introduce extra noise and also just longitudinal jitter of the different components. And so we have to do a lot of noise reduction in this initial pipeline, but we also have to do a bunch of other things. In particular, we have to produce synchronized data streams, because all the 3 spacecraft have their own clock. We have to do some ranging to enable all of this processing, and we also probably have to do a certain amount of instrument characterization. Some of this is just needed to do all of this, but some of this is also needed for the subsequent data analysis. So in summary, this 0.5 to L1 processing, the main purpose is to combine all the interferometric measurements. I tried to do a quick count and came up with 66, but I might have miscounted, with ground tracking information and auxiliary sensors to produce 3 synchronized scientific variables plus a number of other quantities needed for the data analysis. And this is a box that I want to briefly mention, but I will not speak more about it in the remainder. But there are a bunch of things related to that are being presented at this conference. One of them is just noise modeling, understanding how noises enter into this measurement process. And there's, for example, a talk by Leonard this afternoon. Another one is that to do this instrument characterization, there will be input from onboard sensors, and there's a talk related to this in this performance and data analysis session. Something that we might want to do already as part of L0.5 to L1 is detecting artifacts, detecting glitches. And for example, there's a session at the end of this week, and one talk in particular for a fast method using machine learning, which might be suitable there. And there's, of course, also a lot of stuff for noise characterization you can do in actual astrophysical data analysis. But there are many more posters on that I cannot mention here. Now, I give you a very quick overview of LISA. I think you've all seen it. We have these 3 spacecraft with these MOSAs that contain a telescope, an optical bench, and a test mass. And the desired measurement is actually this measurement from test mass to test mass. And the way this is done is that you have these 3 interferometers. You have the science interferometer, the test mass interferometer, and the reference interferometer. And one of the first steps in this pipeline is to combine those to produce the test mass to test mass measurement. And the expression for that is not very difficult. You essentially just add them up with some delays. But I'm especially mentioning it because there's a talk at the end of this week where this was demonstrated in a time domain simulation with real control loops that you can actually reduce the spacecraft jitter in this process. Now I want to speak a little bit about time delay interferometry. I will not be able to give full justice to the history of the subject. It goes back very far. But there's an excellent Living Review article that covers that, and that actually goes back. The first reference in the TDI section comes from 1984 from Piet Bender and Faller. So 40 years this year. So this has a long history, the subject. Somebody asked me yesterday if it's a relatively new subject, and it's very much not. So the basic problem is that if we would construct a simple Michelson interferometer like this, which you could do by just locking the remote lasers, the arm length in these are unfortunately not equal, and they're also time varying, as you can see in this little plot up here, where I show the arm length between the three spacecrafts, which means that laser frequency noise will couple via this very well-known formula. It's essentially a linear scaling to first order. And if we look at what that looks like, the arm length mismatch is about 0.22 seconds. This is the power spectral density. The laser noise is somewhere up here, around 30 hertz per root hertz. And by doing the simple Michelson, you just get down to this level. And we actually want to get down to this level, which is around a picometer. So we're very far away from that. And the solution was first proposed in 1999, as far as I know, so 25 years ago, also a nice round number, is time delay interferometry, where we construct these equal arm interferometer that make complex paths between the spacecraft to construct a constant arm length equal arm length interferometer in post-processing. This is an example of so-called first-generation TDI. And with that, we already get down to this level, which is very close to our 1 picometer curve, but not quite there yet. And I have some more diagrams up here and some formulas you can look at later, how to actually compute the path length mismatch. Now this is also, it's not quite a fair comparison, because by doing these extra paths, you also change the response of the instruments to other noises and to gravitational waves, so you have to look at a different comparison to really evaluate the performance. So for first generation, you have to compare to this curve, but what we're actually using is this very simple path of second generation, which you can see here. It looks a bit complicated here, but essentially you just go along each arm one more time for each of the beams. And that reduces the arm length mismatch further and brings you down to this level here, which is sufficient. You also, again, get a different transfer function, but that's now we reach our requirement with that. And this is the Michelson second generation combination. Now I have a very brief overview of how this actually works. How do we build these variables? And for this, I'd like to present this toy model, where this is simplified view of spacecraft 1, this is spacecraft 2. Each of them you have a laser, which has laser frequency noise. It gets sent to the distant spacecraft and interferes here with the noise of this guy. And what we measure here then is the difference between the two. And we use this, commonly used as this delay operator notation. What that means is that it relates the laser noise of this guy at the time of its emission to the measurement that we take here at the time of a reception. So it just means take the laser noise from this guy and evaluate it when it was actually emitted in this measurement that is taken when it is received. And what we can do with these measurements as a simple toy model step is to just add them up, adding in this delay operator. And since we then have the same noise term, in this case noise 2 appearing here and here, it cancels out in this combination and we're just left with laser 1. Now this particular combination doesn't cancel laser noise, of course, but the trick is now that you can continue doing that, continue adding up measurements. With each step, you construct one step of this photon path. You can do that one way, and then you can do it the other way with an opposite sign. And what you get in the end when you subtract those is something that exactly looks like this cartoon that I showed you earlier. Now in practice, to do this, you need to somehow time shift your measurements after you have taken them. And the way we plan to do that is using interpolation, which I think was first proposed in this paper by Shaddock et al. And the baseline for this has been for, well, 20 years now, Lagrange interpolation, but there's actually some new results here at this conference where people looked at alternative methods. There's one talk by Martin Stab and another one by Wolfgang Kastaun, also in this performance data analysis session this afternoon. Now, I showed you the Michelson variable, and it's certainly the most well-known, but it's not the only one. There's an infinite number of combinations you could do that cancel laser noise. So the question might arise, which one should you use? The good news is that at least for a static constellation, this is very well understood. You can show mathematically that the whole space can be exactly generated by just 4 generators. And there's a similar result for a rotating constellation. And the one set of these generators are the so-called Sagnac variables, which just correspond to these paths going one way and the other one. There are again 3 of them. And the fourth generator is the so-called zeta combination, which is this symmetric measurements between all spacecraft, and it's relatively sensitive to gravitational waves. Now, you can, to exactly represent the space, you need 4 in this scenario, but these 4 are not independent, but only 3 are independent. There's one way to think about it is that there's only so much information you can extract from a triangle. And it means there's this time delay relationship between them, and with that, especially if you express it in the Fourier domain, we think that 3 channels still contain all the information even in the realistic scenario. I put a question mark here and some check marks because there are people looking in the details that maybe there are some edge cases where you might lose something when you just use whatever channels you want. So as I said, the assumption is that even in the realistic scenario, these 3 channels are enough. The popular choice are the 3 Michelson combinations that you've heard a lot about already. And under some actually very strong assumptions that will not be applicable to the real instrument, you can very easily construct these noise and signal orthogonal channels A, E, and E. But even if these assumptions are violated and you can't do that, you can still use these guys and use the full covariance matrix. All of that being said, there are some presentations and talks and posters here where people look at alternatives. There was one already yesterday in the data analysis session on using a combination of these 3 guys that is null to a certain sky direction. There's a poster by Gang Wang, I think it's somewhere over there, on using alternatives to X, Y, and Z, who seem to be more robust. And there's also approaches, and there's a poster on one particular one, that do away with this whole idea of TDI and just try to analyze the raw data directly and look at, because you can see in the raw data these strong noise correlations from the laser noise, and you don't have to explicitly construct these variables. And there's a poster from John Baker et al. From that. Now, that was laser noise, which is the main step we have to do, which is why these TDI combinations are very central in the LISA mission. But there are other noise sources that we also need to worry about. As I mentioned earlier, one of them is clock noise, and it appears because what we actually measure in our interferometers is the interference of 2 beams at slightly different frequency, between 5 and 25 megahertz. And our gravitational wave that we're interested in, and the laser noise I mentioned before, is now a phase fluctuation in the speed node. And to measure the picometer accuracy corresponds to a microcycle at 280 terahertz. You need actually 40 femtosecond per root hertz timing precision, which is very out of reach for existing space-qualified clocks. I showed you a little cartoon over here for the beat node frequencies at megahertz, and you have these very small, this is actually laser noise, which is a pretty big fluctuation. Side note that getting the beat nodes to be in exactly this range, which is needed for technical reason, is actually not trivial at all. But there is a presentation in the IDS session by Javier presenting how we ensure that using something called frequency planning. Now this was precision, and the way we deal with that is to do inter-spacecraft measurements. I will explain them in a bit more in a minute. But before that, I want to give you an overview of the bigger picture. So we have these 3 spacecraft. Each of them carry their own clock. To correct for this clock noise that I mentioned in the last slide, you need to do inter-spacecraft measurements with the precision corresponding to this roughly. These are all very rough numbers. Microcycle, but we also need a certain ranging accuracy for the inter-spacecraft measurements because this is needed for this previous step on laser noise reduction. If you were very keen-eyed, you saw that the delta T for 1 picometer is around 10 to the minus 8, which is 10 nanoseconds. And on top of that, these relationships between the spacecraft, we also need some relationship to a global timescale, which we get from ground tracking, for the data analysis, but also for some steps that we have to do here that I unfortunately don't have time to go into detail. So how do we do this? How do we do these measurements? The way is that on top of the main carrier laser beam, we do 2 kinds of modulations. One of them is a so-called PRN code. It's a sequence of 1s and 0s, so the phase makes little steps. And the other one is a 2.4 gigahertz sideband modulation, which means that the spectrum that comes out of the laser actually looks something like this. So we have our carrier, we have the PRN, the stepwise modulation creates a spread spectrum around the carrier, and we have these sidebands at high frequencies. The whole thing is more or less symmetric, so the laser on the other spacecraft also has this modulation, which is a slightly different frequency. So the beam that is generated here travels over here and interferes with the local one here. And what we then get are 3 beat nodes. We have the carrier-carrier, and we have the beat nodes between the sidebands, which is the reason why these are at slightly different frequencies, so the beat nodes don't fall on top of each other. And we have these pair encodes in the data. So what we can then do with these pair encodes, we can correlate them against the local copy. They're known a priori, and this gives us the absolute range, and these sidebands give us the precision in the measurement. And there's actually a talk on that in the end of this week as well, in the constellation session, in how to design these codes by Pascal Grave. Now, as I mentioned before, this scheme, combining these measurements, gives us something that is at the required level of precision and the required level of accuracy. This is a plot showing you some of the main components. This is the clock before correction, so you can see it's far above this 1 microcycle curve. And this is a plot of some of the other limiting noise sources. This is not a very new plot. It's from about 3 years ago, but the basics are still there, I think. And there are also actually 2 talks that look into how to do this fusion of ranging sensors. There's one by Niklas Reinhardt in this afternoon, and there's another one by Waldemar Martens on Friday. And there's also been a number of demonstrations of this procedure. In particular, I want to highlight the hexagon experiment, where there was just another paper published. It is unfortunately not being presented here, as far as I know, showing the PON and the sideband scheme in a hardware demonstrator. There has also been some related studies of treatment of onboard delays which can cause a bias that is above these 10 nanoseconds. And there's also a talk, also in this session this afternoon, of another hardware simulator that will at some point include these effects as well. Another thing I want to mention quickly is TDI ranging, which is an alternative or supplementary technique we can use to do absolute ranging between the spacecraft. And the basic idea is just that the laser noise only is reduced if you use the right delays. So you can turn that around and minimize the laser noise by tweaking the delays to the right values. You can also go one step further and artificially introduce extra laser noise by doing these calibration tones. This is something being looked at by Martin Stab et al. This is a plot he shared with me, where you can see that he can reduce the noise level down to the level of secondary noises using this technique. And I think there's also at least one poster that looks into TDI ranging at this conference, which I highlight here. Now, that was clock, and now the last noise source I want to speak about is tilt-to-length coupling, which is a very big topic lately. And what is it? I have to say I'm not really an expert on the subject, so I apologize if I misrepresent anything said here. But the basic idea is that if you have an optical system, like it's plotted here, and you have tilted, you do some angular rotation, and you have misalignments in this system, that this will cause equivalent longitudinal path length changes. So these angular tilts will couple into our longitudinal readout. There are a number of mechanisms for that. One of them are misalignments. I think also wavefront imperfections are another one. And there are probably more that I don't know about. You can compensate to that to some extent in hardware, by just compensating for these misalignments using imaging optics, for example. But we also have, luckily, a measurement to compensate for that and to characterize it, which is called DWS, differential wavefront sensing, which roughly works like this, that each of our photodiodes in the interferometers is not just a singular sensor, but it has 4 quadrants, which means that if you have 2 beams incoming that are at an angle, the beat node, in this example, in the upper one and in the lower one, are slightly shifted with respect to each other, and you can convert that into an angular readout. And this then allows you to characterize this noise source. So, and there are a number of presentations and posters related to this topic. There are a few studying, for one, how this appeared in LISA Pathfinder, because there it was already apparent, by Marie-Sophie. And there's another one about simulations for the LISA test mass interferometer, how it will appear there, the poster. Now, this was what the effect is, and now I have one slide summarizing how we can compensate for it in post-processing. The basic idea is that, okay, first the problem is that if you do nothing, we expect this to still exceed our requirements. And the way we can compensate for it is that we have to somehow model how these angles couple into equivalent path length changes. This is not entirely obvious and straightforward because LISA is a very complex optical instrument, but you can model it and then you can try to fit the coupling coefficients. So you assume, what people usually do is that they assume some linear model that each jitter couples into equivalent path length with some factor. As I mentioned, the coefficients are not sufficiently well known a priori to directly subtract it, but what you can do is to, similar to TD arranging, minimize the noise by fitting the correct coefficients. And this is a plot from a publication from Sarah, where they showed that luckily it seems to work, so that's good. So you can see here the 3 stages, including the ground-based compensation in hardware and the post-processing subtraction. And there are also a number of presentations related to that by Sarah and by Jose, how well this works. And another option to just minimize the noise that's there anyway, again similar to TD arranging, is to purposefully inject signals to characterize it. And there's a poster related on this approach. And since it's such a relevant noise source, as you can see, there has been a number of experiments trying to characterize this in hardware demonstrators. There's one talk again this afternoon. And a number of posters related to that. So if you're interested in the topic, watch out for the TTL. I forgot one, sorry. Yeah, that brings me already, I think, to my last slide, which is something I wanted to highlight, that there's actually a focus issue in CQG this year on these subjects on noise modeling and noise reduction for space-based gravitational wave detection, which is pretty much what we call L0.5 to L1 processing in LISA. The target deadline for submission is the 31st of December, but if I understood the website correctly, they accept things as they come in, and they will be added. John Baptiste is nodding, so it seems to be correct. Speaking of John Baptiste, here's a list of guest editors, which I think are names very well known in this community. So if you have any questions about that, reach out to them. I'm sure they're happy to answer them. And surprisingly, I think I was faster than I needed to be. So that's nice. We have extra time for questions. Thank you.
All right. Can we get a microphone over here? And thanks, Olaf, for that lovely talk. Learned a lot. And then there's going to be one.
These 24 tilt-to-length coefficients that need to be measured, do they need to be measured once and then continually refined, or are they time-varying and need to be constantly updated and monitored?
I'm not the expert, so if I say something wrong, please somebody correct me. But as far as I understood, we expect them to drift over time, such that you have to repeat this procedure somewhat frequently. I think once a day or once a week is what people have in mind.
Thank you for the nice talk, by the way. When you were talking about reducing the laser noise, you showed the generators that were basically all circles, except for the one that had those pairs. I was just wondering how to combine this with previous mission proposals where the third arm was removed and you couldn't make those circles. Would that be a problem, or?
I mean, the space of variables that you can construct becomes a lot smaller, because then you're pretty much stuck with the Michelson solution. You still have the Michelson solution, but that's it. And you lose at low frequencies about a factor 2 in, square root 2 in sensitivity, and at high frequencies about a factor square root 3. Yeah, and a lot of robustness to glitches and things like that.
Hi, Olaf. Thank you for the talk. As far as you know, those simulations that shows the reduction of TTL in software and post-processing, are they done with gravitational wave data on, with confusion, noise, and all that?
Yes, I mean, I recommend you to speak to Sarah about the details, but as far as I know, they did inject stochastic signals and were able to still do it.
Am I missing anyone? Can I ask a really naive question? is all of like the TDI reconstruction, all that, does it happen post-process on Earth, or do you have to actually do anything live?
No, we do it on ground because the reason is that to do this efficiently, you need pretty high order filters, this Lagrange interpolation, so it's computationally quite expensive, and you want to do as little as possible on the spacecraft.
There's nothing there. Whoops, that's our timer saying, good timing. We have more questions? We still have a minute? All right. Oh yeah, one more, okay.
Just a quick question. After all the noise is removed from the signal that is beamed out from the aircraft, the spacecraft, how many bits do you think there will be that contain gravitational wave information?
Sorry, I'm not sure I understood the question. Can you repeat?
So we lose orders of magnitude due to noise in the data stream.
Yes.
So if you say you have 24 bits of data and you remove a factor of 1 million in noise, you don't have a lot of bits left. How much gravitational wave information is in what is coming down from the spacecraft?
I mean, so you do have a very high dynamic range in the data. I think that's what you're asking about. I don't know the precise number. I think we did it the other way around. We calculated how many bits do we need such that the quantization noise, given our dynamic range, is below the other noise sources. And I think we end up with 64 bits is roughly the number that you need in the data. And I don't know the number in bits, but you lose around almost 10 orders of magnitude by doing this subtraction.
Yeah, okay, that's fine. Thank you.
Right. Those of you who are still looking for seats, there are seats up here in the middle towards me. And there's still plenty of seats over here to the right, so you don't have to stand back there if you don't want to. Okay, well, let's thank Olaf again for that lovely presentation.